Somebody asked, to see a non-regular language. Is that person here who asked that? Okay. Well, in that case, I'm not going to go into it. We will actually, in not this lecture, but probably the next lecture, we'll see languages that are not regular and prove that they're not regular. So what I was going to do, if this person was here, was just show him one, and then he could go home or you can go home and fiddle with it and try to find a finite state machine for it and fail. And then that will maybe build up your intuition. Actually, let me do that anyway. So try this one. The language is going to be the set of all strings, a to the n, b to the n, where, well, n is the same, it's the same n here, okay? So you have to, n can be anything. N can be n greater than or equal to 0, okay? So what this means is the following, like A, B is in the language because it's the same number of A's and B's. Okay. By the way, this symbol A, that's a member of the alphabet, raised to the n, that just means repeated n times. Okay, that's in the book, but you might not have read that. So A repeated n times followed by B repeated n times. Okay, so that's a language. It's a set of strings. Here's another member of that language, double A, double B. Okay, that's repeated twice. ABA is not in the language, right? Okay, because that's certainly not A some number of times and then followed by B the same number of times because you have this extra A there. Or similarly, AAB, that's not in the language because it's two A's followed by only a single B. All right. So this is a language. It's a set of strings. But I'm claiming that this is not a regular language. You can try to build a finite state machine for this, but you should fail. Okay. And in a couple of lectures, we'll actually prove that there is no finite state machine that can recognize this language. Okay. So fiddle with that if you have time, and that'll build up your intuition a little bit for when we get there. All right, but what I actually stopped with last time was the following claim. Well, let me remind you what the union of two regular languages is. So union of regular language A and regular language B, that's the set of strings X, where X is contained in A, or X is contained in B. Okay, and you notice this or. So when you think of a union of two languages, you can think of that union is essentially talking about an or of two conditions. This is the condition for being, well, this is saying it's in A, whatever it takes to be in A, that condition, or the condition of whatever it takes to be in B. I haven't told you what A and B are specifically, but those are two regular languages. Okay? And then the theorem that I had stated, or the claim that I had stated, is that if A and B are regular, then A union B is regular. Okay? And again, I'm using the fact that A is a set. It's a set of strings, and B is a set of strings. And so as sets, it makes sense to take their union. The A union B is a set of strings. Okay? So we're assuming that A is a regular language and B is a regular language, and we want to show that A union B is a regular language. We'll also, along the way, and I don't know why they don't state this explicitly, but we'll show that A intersect B is regular also. So again, you have two different sets. You can apply set operations to them. Okay, so, but we'll do the proof first for A union B. And what I did last time was to show you a mistaken approach. Okay, we said, well, A is regular. So what does that mean that A is regular? What's the only thing we really know about a language if we know that it's regular? What's the thing I can say about it?
There's a finite state machine that accepts it.
Yeah, there's a deterministic finite state machine that recognizes it. Okay. Yeah, the book kind of it gives you this misdirection. It first defines, it talks about machines accepting a language, and then it says, but don't do that. Don't say that word. Talk about machines recognizing a language. Okay. So we know there's a deterministic finite state machine that recognizes A, and we know there's a deterministic finite state machine that recognizes B. And that's basically all we know about it right now. That's all we know about what it means to be a regular language. So let's say there's this M1 recognizes A, and M2 recognizes B. Okay, and these are two deterministic finite state machines. And then, because the only thing we know about what it means to be a regular language is that there is a deterministic finite state machine that recognizes it, in order to prove that A union B is regular, I have to come up with some deterministic finite state machine that recognizes A union B. All right? So the general idea is that we're going to somehow use these two finite state machines to build a finite state machine to recognize A union B. We want, I'll call it M3, that recognizes A union B. Okay? And last time what I did, which was I said was wrong, is to think about, well, you've got the machine M1 that recognizes A, and you've got the machine M2 that recognizes B, and this is an OR here. The union is really the string X is in A or it's in B, so we'd like a machine to build some kind of machine that would go through either of these, and then if either one of these accepts, if it comes to a accept state or a final state, then we would accept. But we don't know how to, we don't have operations like that for deterministic finite state machines where we can branch two ways, and then if either one of those succeeds, well, this is okay because we could just make these the final states anyhow. But we don't know how to branch two ways. We'll actually learn that today. But right now, we don't have that as an operation. This is a deterministic. We need to build a deterministic finite state machine. So branching like that isn't a possibility. Okay. So, but the idea is that M3 should simulate M1 and M2 running in parallel. However you spell parallel. So this idea of simulation is something that comes up over and over again in this kind of material, that with one class of machines we can simulate another class of machines, or show that a certain language is, in this case it's A union B, is recognized is recognized when we have the components M1 and M2. Okay, so let me just show you, first of all, by example, I hope, how this works, and then I'll show you very formally how this works. Okay. Yeah, all right, so we're going to let A be a set of all binary strings with an even number of zeros. Even number of zeros. And B is going to be the set of binary strings with an odd number of ones. Okay? So let's just see an example in A. We need an even number of zeros, so maybe it's 1, 0, 0, 1, 1, 0, 1, 0, 1. That has an even number of zeros, and so that's in A. Okay? And 1, 2, 3, 4, 5. Actually, this is also in B because it has an odd number of ones. Okay, so this is a string which happens to be in both A and B. But let's say we had 1, 1, 0, 0. That's contained in A because it has an even number of zeros, but it doesn't have an odd number of ones. So that's in A, but it's not in B. Okay? So everybody see what these two languages are. Now I want to show that, and A and B are both regular. It's easy. Let's build a finite state machine for A. Okay, so M1, we even looked at one, I think, last time that does this. It's an even number of zeros. So there's the start state, which is also going to be the final state. There's a 1. This truck is terrible. 1. I'll give it a name, Q1. And then we go over to Q2 with a 0 back here, with a 0, and here with a 1. So this machine accepts the empty string, which has 0 zeros, so that's an even number of zeros. And then you can have any number of 1s you like, but if you get a 0, you can then have as many 1s as you like, but you have to get another 0 in order to get back to the final state. And then you can have more 1s, and So this generates any binary string, but the only ones that it accepts are the ones that have an even number of zeros. Okay? So this is an easy finite state machine for M1. And then for M2, we want a machine that accepts binary strings that have an odd number of 1s. Okay, and that's similarly easy to do. Here's a state Q1. That's a 0, 1. Oh, the book typically uses the same notation for states in two different machines, and that's fine, but it gets a little bit confusing later on when we have to refer to both of them simultaneously, and the book does that by the position in a vector. I like to actually give different state names to different states in different machines, just for greater clarity. So these states will be called Q, and this will be P, and mathematically it doesn't matter at all, but I find it just simpler to keep your wits about you. So this is P2. Okay, so this should be a machine that recognizes the binary strings that have an odd number of 1s. So you can start with any number of zeros. You go over to here. This is the final state. That's 1, 1. You could have more zeros. You go over there. That's an even number of 1s, and this is not an accept state. This is not a final state. So in order to get back to where there's a final state, you have to have another 1, which makes it now an odd number of 1. So this is a machine that accepts the language B. Okay? But now we want a machine that recognizes any string that is either accepted by this one or accepted by that one. And as I was saying earlier, we can't just somehow put them in parallel because we don't have an operation in deterministic finite state machines that does any kind of parallel type branching. So we have to build a third machine that somehow is constructed from these two, but has a different idea. Now, how many people have actually, this is the next page on where I got to last time in the book. How many people have read that? I know some people have. The people have come and talked to me. Okay, but all right, for those of you who haven't, then so again, the idea is to somehow simulate both of these, and the idea is that we're going to build a third finite state machine where its set of states is going to be the Cartesian product of the set of states in M1 and M2. That is, it's going to be all pairs of states where the first state comes from M1 and the second state comes from M2. So the states in M3 are going to be Q1, P1, Q1, P2, Q2, P1, and Q2, P2. Okay? So this object here is a pair of states from M1 and M2, right? But it's also, this object is also a single state in M3. And you just have to, think like a mathematician, as opposed to just, somebody off the street. This is just a funny name, okay? It's a long, kind of awkward name, but it is just the name of now a single object, and there is a single state in M3, even though where we got that name from was from a pair of states from M1 and M2. Okay? And we'll simultaneously, or sometimes refer to this as a pair of states, and then you have to think, okay, pair of states from M1 and M2, or refer to this as a single state, in which case we're obviously talking about M3. Okay? So this is the set of states, 4 states from in M3. And then what's the starting state of this machine we're trying to build? It's going to be that particular pair of states where they're both the starting state. So this is a starting state Q1, this is P1, so it's Q1, P1. Okay? That's the start state of M3. I'll get to the final state in a minute, but now I need to show you what the transition function is. So we're now talking about, again, M3, and so in order to distinguish it from the, well, I guess what I better do is the transition function here was going to be called delta 1, transition function here is called delta 2, and this one, we'll just make it delta 3. Okay. So the transition function, what's a transition function generally? It's a function on what? What are the arguments? Yeah.
The state and the language.
The state and the what?
And if it's like a binary language, then it will be like bits.
Okay, and the term more generally is character in the alphabet. So this takes in a state, okay, in a state and a character, okay, and it goes to a state. All right. Now this is the alphabet. All right. I didn't tell you what the alphabet for M3 is. It turns out the alphabet for M3 is the same as the alphabet for M1 and M2. They had the same alphabet. And so, but to be completely formal and correct, you should say what the alphabet is here for M3 is the same as for A and B. Okay, or sigma for, this is the alphabet for A union B. Okay. So this is what we want. We want a transition function which is over the states of M3 and the characters in the alphabet and go to the states in M3. And we're trying to simulate, remember what we're trying to do? We're trying to simulate what those two different machines would be doing, M1 and M2, whenever they see a particular string. So again, working by example instead of by total formality, we look at each one of these states in M3 and we ask for each particular character that is in that would be processed in the input string, what do these two separate machines do, M1 and M2? So for example, what does, if we look at this state, Q1, P1, and it sees character 0, okay, so delta 3 of this, it's supposed to go to a state in Q3, which means it's a pair of states, one from M1 and one from M2. And it's supposed to be simulating what M1 and M2 would be doing. So you just ask yourself, well, what does M1 do when it sees Q1, when it's in state Q1 and it sees a 0? What does it do? Yeah, when it's in Q1 and it sees a 0, it goes over to Q2. Okay? And what does machine M2 do if it's in state P1 and it sees a 0? Well, it stays in P1. Okay? So this is the first transition rule. If you're in this state of M3 and you see a 0, you go to that state of M3. All right? Let's just do another one. Well, before I do another one, let me ask, how many transition rules will there be for machine M3?
8.
Yeah, 8. Exactly, because we have 4 states, and we have an alphabet of size 2, and so it'll be 4 times 2, which is 8. So let's just look at what's delta 3 of, let's say, just take the second state here, Q1, P2. Q1, P2. Okay, and, well, I guess I should have also said what happens when you see a 1 here. We'll look at that in a minute. And we'll look at what happens in a 0, 1 here. Okay, so what does happen in Q1, P1 when you see a 1? So you go over here and you say, well, what happens when you see a 1? You stay in Q1. What happens when you see a 1 here? You go to P2. So it's Q1, P2. This would be Q1, P2. All right? And what happens if you're in Q1, P2 and you see a 0? Well, what happens if you're in Q1 and you see a 0, you go to Q2. And what are we at? P2. If you're in P2 and you see a 0, it's a P2. So what was that again? What did I just say? It's Q2? And what? P2. Okay. And what happens here? It's what? P1? No, it can't be P1. Q1, P1? I don't know. I'm not processing it. Is that right? How many people? We'll do crowdsourcing here. How many people agree with this? How many people disagree with this? Okay, and how many people didn't answer? Okay, and why? It's what? Okay, all right. Okay, but does anybody disagree with this? All right, well, you can check it out at home or, anyway. As long as you get the idea now, you can build the transition function, okay? And now what's the final state for this machine F3, or the final states? Well, we're looking for an OR, okay? It's the union of two languages, so it's the OR. So if either of those machines reaches an accept state, then you want to accept. So what are the states from M3 that have the property that one or the other, or perhaps both of these machines, M1 and M2, accept? Well, it's if you're in a state Q1 and either P1 or P2, or you're in P2 and Q2. Okay, so it's Q1, P1, or Q1, P2, or Q2, P1. And it's getting a little crowded down there. Q1 with P1, or Q1 with P2, or Q2 with P1. Those are the three states of M3 that are the accept states for the language A union B. Okay? Why are there only three and not four? You might think there should be four, right? Because it's Q1, and anything from here, that's 2, and P2, and anything from there, that's another 2, and that makes 4 altogether, but we only wrote up 3. Yeah, because the Q1, P2 came up in both of those cases, all right? And so we only need to write it down once. It's wherever that was, yeah. Q1, P2. Okay? Yeah?
For the final state, the last set shouldn't be Q2, P2?
Q2, P2. Oh, did I write this wrong? Okay.
The last one.
Oh, I see. Yes, yeah, I did write that wrong. Thank you. Yeah. It's a P2 because the P2 is the accept state from M2. Okay. Now, this describes the transition function. It describes the final state, the start state, the set of states, the alphabet. So I've completely described a finite state machine, a deterministic finite state machine. Its transition rules, everything is there. I could try to draw this as a diagram here of one thing like this, but it'd be kind of messy. And so it's often the best way of describing a finite state machine is just through the listing out of the transition function. I could put the transition function in a table also. That's another way of displaying it. But anyway, all the information is there to describe the finite state machine. Now, why does this work? Why is this the finite state machine that accepts A union B in this particular case? Because what it's really doing, if you feed a string into this finite state machine, what it's doing is it's essentially running both of the machines, M1 and M2, in parallel. It's keeping track of what M1 would be doing as it's processing the string, and what M2 would be doing as it's processing the string. It's doing that by having these two states put into one state. The two states of M1 and M2 are joined together as a pair to be a single state of M3. And every time that the machine M3 makes a transition, it's really basically saying, what would M1 do and what would M2 do on that particular character, and just recording it in the pair here that names a state of M3. Okay, so if you get that idea, and then here the final states or the accept states are any pair of states that has an accept state either from M1 or M2 or maybe from both. If you get that idea, then it's obvious that this is right. And in fact, the book, I think here at this point, maybe it's in a different one, has a theorem and then a proof. It says proof, P-R-O-O-F, and then it starts telling you something about it, and then it says it's obvious, which in my mind is not a proof. I mean, if you're going to say it's obvious, then that's you might as well just do it without saying P-R-O-O-F. But this is obvious once you get the idea of how this works, how this is simulating, how it's really recording what both of those machines, M1 and M2, would be doing. Let's just work through a small example, and hopefully it'll all crystallize. So again, oh, I just erased what this language is. This is the language of strings that have an even number of zeros or an odd number of ones. So it's an OR, so even number of zeros. Let's take that one, okay? An even number of zeros. Well, not in this lifetime, anyway. Not in this universe. Okay, an even number of zeros, but also an even number of ones. So this is in A, right? But it's not in B. But it does mean that it's in A union B. Okay? So this string is in A union B. So if we process this string, let's call this W. So we want the computation of M3 when we give it W. So what state do we start out in? Yeah. Q1, P1. That's where we start. Okay? And then we see a 0. So what state do we move to? I can tell this example is going to overwhelm me. I'm not good at doing examples on the board. I get tired. But Q1, P1, we actually did figure that one out under a 0, is Q2, P1. Q2, P1. Sees a 0. And why? It's because the machine M1, if it was in state Q1 and it sees a 0, it would move to Q2. And machine 2, if it's in P1 and sees a 0, it would go to P1. Okay? So we've just simulated the first step of both M1 and M2. That's what M3 is doing. It's simulating what the two different machines would do. And then we see a 1. Okay? If you're in this state, Q2, P1, we didn't write that out before. Q2, P1, you see a 1. But to figure out what M3 does, what's the rule for M3, it's, well, what does M1 do if it's in state Q2 and sees a 1? That's a Q2. And if you're in P1 here and you see a 1, you're in P2. So it's Q2, P2, if I'm right. Q2, P2. Okay, that's when it sees a 1. And then, we'll go back this way, the next one is a 0. Okay? Well, this is getting tiresome, but everybody get the idea? We're basically, the M3 is simulating both M1 and M2, and when it finally processes this last one here, if you do this one, do this at home, it'll crystallize better. You should be in the final state. Yeah, let me just, well, you're going to ultimately be in a state which is accepting for A, and we know the accepting state for A is Q1. Okay? It's not an accepting state for B, so what state would you be in if you're not accepting for B? It would be P1. So this is my claim. If you actually go home and crunch on this and walk through these various rules, on this particular string, you should end up in Q1, P1, and that's an accepting state for M3. Q1, P1. It's a final state or an accepting state for M3. Okay. Now, this little example I made up, so it's not in the book. You should just, write down what the language is, and then you can do all this reconstruction yourself and check this one out. And in fact, maybe I'll make that as a homework. Part of the next homework is to check out this string, show me the actual computations that M3 would do. Okay. So let's now, so I have to write that down if I'm going to do that. So 0, 1, 0, 1, 0, 0, 1, 1. Okay, so let me just try to write this down more formally, what it means for to build the finite state machine that accepts the union of two languages. So a more formal definition page 1, page 2, page 3, page 4. Okay, so this is delta for the union. Okay. Well, all right. First of all, the let's just say 3 represents the machine for the union of the two. Okay, so this is going to be the set of pairs R1, R2, such that R1 is in Q1 and R2 is in Q2. So Q1 is the set of states from machine M1, Q2 is a set of states from M2, and the states from M3 are just those pairs. Okay? So this is just writing down in more formal mathematical notation what we just did over there on a particular example. And so another way of saying this is that Q3 is equal to Q1 Cartesian product with Q2. Well, that's the Cartesian product. Sigma is the same. Okay. And Q0, that's the start state for Q3, is well, let me just write this, because even the book is inconsistent about what's the subscript for the start states. If the book had always said every start state is always Q0 or subscript is 0, that would be okay, but we're not being consistent here. So I'll just say that the start state of M3 is the pair of start states from M1 and M2. Okay? Which again we saw by example. And then the most important specification is the transition function. The transition function for the machine 3 is R1, R2 under symbol, say it's a binary alphabet, is equal to delta 1 of R1, 0, and what goes in here? Yeah, delta 2 of R2 and 0. Okay? And similarly for 1, or more generally, more abstractly, we could just say X. There's that mysterious X again, where X is some member of the alphabet. Okay? So this is just saying what you do in the machine M3 when you see this particular pair is simulate what the other two machines would do when they're in those particular states and they see that particular character, X. Okay, and then the final state, or set of final states, is R1, R2, such that R1 is contained in F1, or R2 is contained in F2. Okay? So you're simulating, M3 is simulating those two different machines. And we're talking about the union of two languages, which means we'll accept the string if it's accepted either by machine M1 or it's accepted by machine M2. And that's why we have an or here. If we end up in a state in M3 which has an accept state from F1 or an accept state from F2, a state from F2, then we should accept in M3. That's the OR. Okay, that's the complete formal specification. And on your homework, you have questions, I think it's like 1.4 or 1.6, something like that. The questions in that series ask you, oh, sorry, they ask you about ands. We'll get there, we'll do ands in a minute. Okay, so this is union, and I claim that this is essentially, if you write this down nicely, what we just did, and you throw in some explanation for why this is right, that's a proof. Okay, and in the book they started to do that, but then they said, okay, but it's obvious. I mean, which is essentially right. If you think about this, it'll just become obvious that this is correct. How many people find this obvious so far? Okay, or if you didn't find it obvious, how many people at least have gotten it at this point? Okay, good. All right. So the rest of you will get it when you think about it in the privacy of your own mind. All right, so that shows, what I've just been doing is a proof, a demonstration, it's a constructive demonstration of the fact that if A is regular and B is regular, then the language A union B is regular. It also shows you constructively how you can build a finite state machine that's for the union of two regular languages. Oftentimes, for example, in this case, the two regular languages are both very, very obviously regular. Did I just say two regular languages are obviously regular? The two languages are obviously regular. There's this simple finite state machine for each one of them. It's easy to construct them. But it isn't immediately obvious how you wouldn't just be able to write down necessarily the union of those two. But this proof gives you a procedure, a mechanical procedure for getting the finite state machine that recognizes the union of those two languages. So if you have a homework problem or exam problem that asks you for the finite state machine that accepts the union of two languages, then you can go through it mechanically if you don't just immediately see how to do it anyway. You can always solve things by the seat of your pants if you're good at that, but here is an actual procedure which you can use, or it tells you more generally that the union of two regular languages is regular. Okay, what about the union of three regular languages? You have A, B, and C are three regular languages, and now I'm interested in the language which is A union B union C. What about that?
Wouldn't it still be regular?
It's what?
Wouldn't it still be regular?
Okay, why?
Because you can think of A union B as another language D, which is regular.
Yeah.
So then it's just the union of B and C.
Exactly right. That's a good way of doing it. And in a sense, what you're doing is a kind of inductive argument. So if A, B, and C are regular, then I was asking about the language A union B union C. And what was pointed out is that you can think about it this way. A union B, we just proved that's a regular language. Okay, so that's now some regular language. We could call it D. And then what we have here is D union C. That's the union of two regular languages, which we just proved is regular. So the union of three regular languages is regular. Okay? And if I ask you on the exam whether the union of five regular languages is regular, that should be an easy question now. Okay. All right. Now what about the intersection of two languages? Okay, so we have A and B are regular. Okay, what about A intersect B? Remember, a language is a set of strings. It's a set. These are two sets, so you can do set operations on them. So you can take the intersection, A intersect B. Okay? If I wanted to prove that any language, if whenever A and B are regular, A intersect B is regular, of course, the only tools we have available are the same kinds of things we were just doing. We know there's a finite state machine for A, we know there's a finite state machine for B, and I'm trying to construct, in general, a finite state machine that recognizes A intersect B. Okay? Any suggestions? Right. Okay. So what's suggested is that you do the same thing. You still want to simulate the machine for A, M1, the machine for B, M2, but now the accept states are different. The final states are different. And what are they? I don't mean in this specific example, but yes, that would be what it is in this specific example. But in general, how would you describe it? Yeah.
You could say it's the Cartesian product of like F1, F2. So every pair of states such that both of them are a final state.
Yeah.
In their respective machines.
Right. So here, F is going to be F1 cross F2. And so essentially, this is an and now. It means you have to be in a final state for the first language A, and you have to be in a final state for the second language B. So the entire construction is exactly the same, except for here, F, you change this or to an and. Okay? And this is what I was saying earlier. The union really corresponds to an or of conditions. The intersection corresponds to an and of conditions, and this is where you see that actually taking effect, the difference between or and and. Okay, so the intersection of regular languages is regular. And your homework, 1.4 or 1.6, I don't remember which, asks you to show particular intersection, languages that are intersections of regular languages, to come up with a deterministic finite state machine for those. And again, you can do those by the seat of your pants, although I think it actually asks also for the finite state machine for each of the individual languages. So you have to do those. But if you then just see how to put them together just by insight, that's fine. Otherwise, you can go through this mechanical procedure and come up with a deterministic finite state machine for the intersection. And sometimes after you do this mechanical procedure, you can recognize that there are some simplifications as well. The machine doesn't have to have all of those. It doesn't necessarily have to have all the transition rules. Sometimes you can see a simplification. Okay, is that clear? Good. Now, nobody said no, so it must be. So now I'm finished what I had intended to do on the first lecture. Now we can start the second lecture. All right. Oh, yeah, well, I want to say one more thing that relates to the homework. So now you have the tools to do about the first half of the questions, and we hopefully we'll do enough in the rest of the lectures you can do the rest of them. The very last question in the homework, I think it's 32, something like that, 1.32, asks you about some computation on matrices. All right. So I don't want to be completely specific about this, but like a binary matrix, something like that, and it asks you about doing computations. I think it actually asks you to do the and, to do the sum, sorry, of something like. Anyway, my point is that it turns out that in that problem, okay, each one of these columns is a character in the alphabet. So the column, a column of binary numbers, is a single character in the appropriate alphabet. So the alphabets, all I want to point out is that alphabets don't have to look like, the English alphabet or the ASCII alphabet. They're just a set of objects. In this case, the objects are columns that come from a binary matrix. Okay? And so when you look at that problem 32 and you're confused, where's the alphabet? What is this machine computing on? Each of the columns is actually an element in the appropriate alphabet. Okay? All right. And that's sort of similar to what was happening over here, that these state names were a little bit odd. And as I said, if you think like a mathematician, it's okay that names look a little weird, or that elements in an alphabet look a little weird. They're just sets of the appropriate type under the appropriate conditions. Okay. Now we're going to, the way the book proceeds at this point is to talk about concatenation of two regular languages. First of all, what is concatenation? Of two regular languages. Okay, so A is regular and B is regular. The concatenation of those, written this way, A circle B, it's the set of strings x, y, where x is contained in A and y is contained in B. Okay? So let's just take these languages over here again. One was, A was the set of strings that had an even number of zeros, and B was the set of strings that had an odd number of ones. So if I have 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, okay, this string is in A, right? Because it has an even number of zeros. And this string is in B, okay? So I can think of this string as x followed by y, where this is x and this is y. So basically we're saying that a string is accepted, or a string is in the language A dot B, if there's some way of breaking up that string into a first part and a second part, where the first part is in A and the second part is in B. Okay? So I'm not sure I can think of a string. Well, yeah, let's just try that one. Yeah, okay. Let's try that string. Is that in the language which is the concatenation of A and B? Or A and B are those? Okay, how do I break up that string? Yeah.
I have to start with the empty string.
Yes. Okay. So I thought that was going to be anyway. Yeah, you're better than I was. Yes, I can break this up. Here's the empty string x, which has an even number of zeros, and here's y, which has an odd number of ones. So in fact, this one is in the language too. Okay. I was expecting it not to be in the language. Even number of zeros and odd. Anyway, try finding one that's not in this language of A concatenate B. Okay? All right. Now we want to prove that if A and B are regular, then A concatenated with B is regular. So here's a claim. A regular and B regular implies A concatenated with B is regular. Okay? And anybody have any ideas of how to do that? Well, again, as we saw in union and intersection, the only tools we have at this point, well, actually it's not true, but anyway, the basic tool we have is that we know there's a finite state machine for A, there's a finite state machine for B, and we have to try to build a finite state machine for A concatenated with B. Okay? Now you might think then, well, what we should do is have M1, and here's a final state, or here's the set of final states for M1, and here's M2, okay, and here's the start state. And so You go on there. But first of all, we don't have anything that does that kind of thing. Okay? Now, if M1 only had one final state, we could also make that the start, join these and make that the start state of M2. Okay? But still, with a single machine, you know when you're done with the computation because you've exhausted the string. You're finished processing the string. And then you ask, am I in the accept state, in accept state or not, to decide whether or not the machine has accepted that string. Here, if we did something like this, we're saying we're going to process part of the string W, and if we're in an accept state here in M1, we'll go on to M2 and start processing the rest of the string in M2. Okay? But how do you know whether you should go on or not? If you're not finished processing the whole string, you don't know what to do about it. So this construction doesn't work. Okay? This construction would accept all of the, if we could at least finesse this problem, it would accept all of the strings in A concatenate B, but it might also accept some strings that are not in A concatenate B. It could get messed up. Anyway, that doesn't work. Maybe what I just said about why it doesn't work isn't quite right. But anyway, it doesn't work because we don't know how to put together two machines like that. And the computation wouldn't know when to move from, effectively how to break the strings into two parts. It doesn't know which is the first part and which is the second part. But we will see later, probably not today, we probably won't get to it, that A concatenated with B is in fact a regular language. Okay? Yeah?
Doesn't M3 work?
It doesn't have to what?
Doesn't M3 work?
What I just wrote up? No. The machine that I just wrote up doesn't work because we don't know how to really put together two machines. That was one problem.
No, but the M3 that worked for the previous example.
Oh, you want to do, okay, you want to take the cross product. Yeah, okay, let's think about this just a minute. Okay, so we try to build the machine that we were talking about earlier for the union intersection. So it's going to have, the states are going to be the cross product of those. But no, that won't work because what that's doing is what the machine that we had built earlier, it's processing the input string both in M1 and M2 at the same time. So as a character of this input string is being examined, M1 effectively and M2 both are going through their computations. What we want here is that M1 should go through a computation on some initial part of the string, and then M2 should go on a computation on the remaining part of the string. Okay? And that's different than what we were doing in the earlier construction because that was processing, both of those machines were operating in parallel. Okay? And that would end up either saying, well, the entire string is going to be accepted by both. It would end up being either the union or the intersection. It wouldn't be the concatenation. Okay, but we will get to how you build a machine that accepts the concatenation. And what I was intending right here, what the book intends right here, is just to show you that what the obvious thing to try is doesn't work. Okay. All right. So all of this leads into a new type of machine called a non-deterministic finite state machine. So up until now, we've been looking at deterministic finite state machines. And now we want non-deterministic finite state machines. So this is abbreviated as NFA. Non-deterministic finite state automata or machine. A is for automata. And these are usually, instead of written as M for machine, usually written as some N with maybe a subscript for non-deterministic okay, that emphasizes the non-deterministic. And the essential thing about non-deterministic machines is that you can choose. If you're in a particular state and you see an input character in the string, instead of knowing deterministically what your next state is, there can be a set of next states that you can go to. So you can branch in multiple ways. You can choose which next state you want to go to according to the transition rules. So the transition rules give you choices. Now later I'll tell you what a computation means, and you'll see that it's not really a choice. It's basically a parallel computation. You're going to do all of them. You're going to take all the choices. 27. Okay, so I'm going to start with an example. Okay. Where's all that talking coming from anyway? Is that the next room over there? Jeez, that's really annoying. Okay. Q1, 0, 1. So far this looks like a perfectly normal deterministic finite state machine. You have a start state, which is Q1, and then not a very interesting machine. By the way, what language does this recognize? That's kind of a trick question. It doesn't recognize any language because it doesn't have a final state. Okay, so it recognizes nothing, not even the empty string. Okay, and then Q3. Okay, so what looks different? Anything looks strange about this finite state machine? Yeah. Yeah, there are two different ways of going. If you see a 1 here and you're in Q1, you can go that way or that way. Okay, we never had that before. Before it was all of our finite state machines were deterministic. You could only go one way. Now it looks like you can go two ways. Here, this looks deterministic and this looks deterministic. That's fine. You're going to go from Q2 to Q3 if you see either a 0, 1, and same thing over there. Okay, but now we have this choice. Effectively, what is a choice? If you're in Q1 and you see a 1, you could go either to Q1 or you can go to Q2. Although the real way of thinking about this is that you go to both. Okay, that the way the book wants to talks about this is that if you're in state Q1 and you see a 1, then you spawn off a new machine. You now have two machines you're conceptually thinking about. One which went this way, okay, and the other one which went that way. And so now you have these two different machines that are running now in parallel on different computations. They made different choices. And then if the machine that went this way, let's say, so it's back in Q1, and we see another 1 in the input string, then again it can choose to go either this way or go that way, and now we would spawn off a third machine, and now we have 3 machines running in parallel. Okay. Does this remind you of anything from physics? Anybody studied quantum theory or at all? Anyway, there this idea of parallel universes where every decision or act that we come to in our lives, or that nature comes to, or if there were some multiple possibilities of what happens, they all happen, but in different parallel universes. Okay, so we're just going down one particular instantiation of all those possible universes. Well, I don't know whether you believe that is true in physics or not, but it's true in non-deterministic finite state machines, that the computation in a non-deterministic finite state machine really corresponds to this set of computations, all the different possible computations that are implied by this, that are specified by this particular finite state machine. Okay, so in fact, let's look at this machine. Actually, it's a different machine now. Why did I do that? Okay, so this is a different machine, very similar. 0, 1, 1, Q2, 0, or the empty string, Q3, 1, Q4, 0, 1. All right, so this one has a new element that we haven't seen before. It still has that choice of what you do on 1 when you're in Q1, but over here it has this epsilon, the empty string. Okay? So if you're in Q2 and you see a 0, you go to Q3. If you're in Q2 and you see a 1, what happens? Well, the machine dies because there's no... actually, that's not quite right. Okay, let me forget the 1 for a moment. If you're at Q2, what this is saying, if you see a 0, you go on to Q3. But it's also saying that if the next character after here, whatever it was that got into here, you can think of that as being the empty string. So you're permitted to go from Q2 to Q3 without consuming an additional character of the input, without looking at an additional character of the input. Okay? So if you get to Q2, you can either consume 0 if that's the next character in the input string and go on to Q3, or you can just go on to Q3 anyway because the empty string allows you to move to Q3. And you don't move, you don't consume or examine the next character of the input string when you take that option. Okay? It's like a get out of jail free card in Monopoly or something anyway. You can move from Q2 to Q3, or actually more like Candyland, where you have to, you're one of those ladders that takes you to some of these, yeah, whatever.
Do you have to consume a 0 if it's looking your gut?
No. Okay. So the question was, if you're in Q2, let's say you got there here's the part of the string that you've consumed so far, and the next character is a 0. Okay. Do you have to take that 0 and go over to Q3? No, you don't. That's one option. That's an option that's available to you to take that 0 to consume it and go over to Q3. But another option that's available to you is to take the empty string and go over to Q3. So let's say we had this. In one computation, if you take the 0 here and you go over to Q3, then what's your next character in the input string? It's 1, right. But if you're in Q2 and you take the empty string and go over to Q3, your next character is a 0 because you haven't consumed it yet. Okay? And in a non-deterministic finite state computation, you do both. You're here and you spawn a new machine so that you can do the 0 in one case and do the epsilon in the other case. All right. So the thing I haven't told you is, what about accepting? What does accepting means? The machine, the non-deterministic finite state machine, accepts some input string W or omega if at least one of the computations accepts W. So because of the choices you have here, because of the epsilon you have here, you have more than one single computation whenever you're seeing a string W. And if any one of those computations accepts, then we say the non-deterministic machine N accepts W. So let's start playing, just to make this really concrete. Let's take W equals 0, 1, 0, 1, 1, 0. Okay? And let's see what this machine does on that input. Okay? So we start out in what state? Q1, obviously. There's still just one start state, Q1. And then we see a 0, right? That's the first character of the input. And what does the machine do when it sees a 0? It goes to Q1, right? So Q1. This is a computation. That's the machine. This is a diagram of the actual computation that's happening. And I'm going to really run out of space if I make these so big. So Q1 goes on to Q1 if it sees a 0. Okay? When it sees a 0. And then from this state Q1, what's the next character we see in the string? Or at that state, we see a 1. Okay? So now the machine is supposed to go two different ways. It's supposed to spawn off a new computation so that it can go both of the ways because of this non-deterministic choice. So in one of those, it can go to Q1, and in the other one, it goes to Q2. Okay? So now we have two computations running. And again, you can think of this as parallel computations happening in a parallel machine, parallel computer. And Q1, and I wrote this down. Oh my God, I have to engage my brain. I wrote it down wrong. Okay, so if we're in Q1 and we're processing this string, we've looked at 0 and 1, and now we see another 0. So what do we do in Q1 when you see a 0? Well, that's deterministic, so that goes back to Q1. Okay. What happens when you're in Q2? Oh, I see. So this really wasn't right. Well, this wasn't quite right. And that explains my notation here. What the book wants to say is you could also go to Q3. If you're in Q1 here, and you next see a 1, it writes down a Q3 here. How did that happen? It's what?
It's you take the empty.
Well, yeah, the first thing is you're in Q1 and you see a 1, so you go to Q2. But Q2, you can take the empty string to go to Q3. Now, I wouldn't have written it that way. I would have said, I put some explanation here. This is, you're getting to Q3 via Q2 and taking the empty string. So that's how you're getting from Q1 to Q3. Or I would have really said you're going from Q1 to Q2 and then you're taking the empty string. But all right, that's the way the book wants to record the possible computations that are happening. Now from Q2, okay, when you next see a 0, if you're in Q2 and you see a 0, then you go on to Q3, and right, and so on. From Q3, everything's get messy, but you could go to Q4 when you see a 1, okay? That's that one. And then you can go to, you can consume these two while you're still in Q4, and you end up accepting. So if you draw this whole thing out, and the book has it, you'll see that there are several different paths of computations that bring you to an accept state. Yeah.
So Q4 is accept?
Q4 is the accept state. Yeah, thanks. Yeah. So main point is that the choices that you have, the non-deterministic choices that you have, what you want to think about that is you're taking all of them, which means you're spawning off new machines, and that means that there's some big tree like this that is explaining all the different computations that this non-deterministic machine can do. And the non-deterministic machine accepts a string if any one of these computations accepts the string. Okay? And in this little example of partially drawing out the tree, we saw a path, a computation in here that led to an accept state. So this string is accepted by that non-deterministic machine. Yeah?
Does Q3 not have a 0?
Yeah, so Q3, so that's where I remember when well, okay. If you're at Q3 and you see a 0, then what happens? The computation dies, and you're in a non-accept state. So that's a reject. Okay. So if you see a Q, you see a 0 at that point, then the computation ends. Yeah.
What if Q3 were an accept state and you saw a 0 and the computation died? Would you still accept or not?
Well, it depends on whether you're at the end of the string or not. You only look to see whether you've accepted or rejected in a. When you're in an accept state, you only end up accepting because you've finished processing the string. Okay. But if you ever get stuck and you can't proceed at all, that's a reject. Okay. Yeah.
So does only that part of like this tree structure die and the rest of it?
Yeah. Okay. So that is a good point. Since this is a non-deterministic machine, only that one computation dies. Okay. The computation that ended up in Q3 and saw a 0, that's dead. But the other computations may be perfectly fine because they're not there seeing a 0. And again, if any one of those computations ends up processing the string and ending up in the final state, that's an accept of the string by the machine. Yeah. Did you have another question?
No.
Oh, it looked like you were. Okay. Okay, so that's what a non-deterministic finite state machine looks like. Now, here's a question. Is any deterministic finite state machine, automata, a non-deterministic finite state, what did I say, NFA? I see somebody nodding yes. How many people say yes? How many people say no? Why? Okay, yeah, the deterministic one cannot split off. But, okay, well, the question, I've got 2 minutes. If you have a deterministic finite state machine, does it satisfy, because I haven't given you a formal definition of an NFA, but does it seem so far like it satisfies? Yeah.
Can it be thought of as a branch, just one branch of the NFA?
Yeah, okay, so the answer is that you can think of a DFA as an NFA, it just doesn't ever happen to have any choices, and it doesn't ever happen to use an epsilon in there. Okay, so it's more limited, but it doesn't do anything that violates what we've seen that an NFA can do. Okay, and if I had time, I would write out the formal definition of an NFA, and I'm just going to tell you to look it up in the book. And you'll see that every deterministic finite state machine is certainly an NFA. Okay, don't go yet. We still have a minute. Is any NFA, well, okay, is any NFA a DFA? No, that's not true. It's not a DFA if it has branches, because deterministic finite state machines don't allow that kind of choices. But final question here is, can the set of NFAs, no, I'll put it differently. Is there a language that can be accepted by an NFA, a language that can be accepted, can be recognized by some NFA, but not any DFA. Okay, so the set of non-deterministic finite state machines, since that contains all the deterministic finite state machines, non-deterministic finite state machines can certainly accept all regular languages, recognize all regular languages. Can they recognize some language which is not regular, is my question here. And we're over time. Anybody want to offer a guess? Yeah. Yes, it seems like they're more powerful. It seems like you can do more with a non-deterministic finite state machine than you can with a deterministic finite state machine. It just seems intuitive that they're more powerful. But it turns out they're not. And that's the next lecture, which will prove that any language that's accepted by a non-deterministic finite state machine can also be accepted by some deterministic finite state machine.